Hi. Today I want to talk to you about Stanyl Polyamide 4.6, the most successful high-temperature polyamide in the world. Over the last 30 years, Stanyl has become a household name in the industry because of the unique benefits it brings to our customers. Let me explain you briefly why Stanyl offers those benefits in a wide range of applications, ranging from cooking utensils used in hot boiling oil all the way to challenging automotive applications inside the automotive combustion engine. The success of Stanyl Polyamide 4.6 opened a new class of materials, the high-temperature polyamides. Over the years, DSM has developed a wide range of products under the Stanyl brand, specific for electronic connectors market and many automotive application fields. These products range from glass fiber reinforced, carbon fiber reinforced, aramid reinforced, lubricated grade, flame retardant grades, and for all kinds of processes like injection molding, blow molding, extrusion, and even for fiber spinning. The invention of our Diablo technology allowed parts made out of Stanyl to be exposed to temperatures up to 230 degrees C for a long time, up to several thousand hours, which was a breakthrough innovation for DSM, allowing the automakers to downsize their engines even further and allow higher boost pressures in their cars. In the high-temperature polyamide arena, DSM added additional polymers like PA4T, a semi-aromatic polyamide, and lately also the highest TG polyamide available in the PPA world, 4T-ACE. So why is Stanyl such a good material that is leading the pack already for 30 years? Well, there are two unique reasons why Stanyl offers three unique benefits. Firstly, it is a very symmetric polymer, meaning that the distance between the amide groups is always the same, which allows the polymer to easily form crystals in all directions. It zips in both ways, no matter what the orientation of the molecule is. Molecules find each other easily to form crystals. Secondly, the amide density is the highest of all polyamides, meaning a lot of hydrogen bonds per volume unit. Those two characteristics result in very fast and high crystallization levels up to 70%, with very fine spherulites and a lot of hydrogen bonds. Now we understand why Stanyl has a much higher crystallinity level compared to other polyamides. And it is this high crystallinity in combination with the high amount of hydrogen bonds that result in those three unique benefits. The first benefit is high temperature mechanics above the glass transition temperature. The second benefit is excellent wear and friction performance. And the third benefit is extremely good flow behavior in combination with mechanical properties. The highest value with Stanyl is created when a customer application needs two out of those three unique benefits. In that case, Stanyl is often unbeatable, like the combination of high-temperature mechanics and wear and friction performance, or high-temperature mechanics in combination with good flow, resulting in weld line strengths and capable for reflow soldering. In those situations, Stanyl is unbeatable. Let's zoom in on those three benefits, starting with the high-temperature mechanics. The high-temperature mechanics all relate back to the high crystallinity level of Stanyl. The high stiffness above the glass transition temperature, which is shown in the graph here, is a result of this high crystallinity level. So you see that the performance on stiffness of Stanyl above glass transition is the highest of all polyamides. Next to that, it shows low creep above the glass transition temperature and good fatigue resistance. It also shows good heat performance in oil and air aging, and it has a little loss of properties between 85 and 265 degrees Celsius. The second benefit is about wear and friction. Stanyl shows a very high abrasive resistance, which also relates back to the high crystallinity. And this allows this material to be used in many applications where wear and friction performance plays an important role. For instance, gears or engine valve timing systems, or applications where scratch resistance is very important. Where other wear and friction materials fail when using in demanding application conditions, Stanyl will deliver smooth and reliable performance. The third benefit of Stanyl is the flow behavior. The high melting point and aliphatic polymer structure result in good flow behavior. That allows users to go to parts with very thin wall thicknesses, up to 0.1 millimeter. That in combination with also very good mechanics. So tensile strength is still at a very high level, even though the flow length is very, very long. The intrinsic high polymer properties allow low glass loadings, resulting in better flow properties. So in summary, the main characteristics of Stanyl are the excellent high temperature mechanics, the excellent flow behavior, and the excellent wear and friction properties.